All right, so we're talking about white blood cells, right? I'll be honest with you, I don't know where I got to last time. So I think we just started talking about, because we're running out of time, right? We have like two types of cells. We have cytes and fills. We have monocytes and lymphocytes, which are two types of white blood cells. Then we have two fill cells. We have actually three fill cells. And I think I was starting that last time. We have another one that's called a basophil. And the fill cells are named for the way they stain, right? So a lot of histological stains basically cause their color based on their pH, okay? And so that's why these are named the way they are. So neutrophils means that the pH is neutral in stain. So it's kind of a bluish purple stain. It's more like a purple stain, kind of in the middle of the other two colors. So it has a cytoplasmic pH or a pH of its granules or its vacuoles are about 7 or just above 7 as far as pH goes. That's why they're called neutrophils. Eosino means acidic, right? So that these eosin actually is a stain, and that's why they're named this. Histologists named it they're eosinophils. Eosin is a stain that stains acid structures that are low pH. So the granules inside of the eosinophil are red because they are low pH granules. Where the basophils, if you look up a picture of a basophil, I'll throw one on the slide on the lecture when I make the video, is going to be completely blue. You won't even see the nucleus. So the granules are bright blue color, and that blue color represents high pH. And so that's why they're called baso, because it's basic. They have basic granules. So eosinophils have acidic granules, neutrophils have a neutral granule, and then basophils have a basic granule. And they're often called granular cytes, is the name they like to give the fill cells. Granulo, that means they have grains or granules that make up their cytoplasm. And you can see that, right? They're really grainy. You can barely see the nucleus here. Whereas the granules here don't really show up because they don't stain as brightly because they're neutral. And then the basophils, it's all blue granules that you see. So now a couple of these cells can be phagocytic, right? So you can also break them down from granular cells to cyte cells or fill and cyte cells. Or you can call them phagocytes and then chemical weapon producing cells. They actually produce compounds that they release into the environment that then help with inflammation and immunity. So your two major phagocytes are monocytes and neutrophils, but there are a group of lymphocytes that are also phagocytic. And so they have the ability to run into things and then ingest them through endocytosis, or what we call phagocytosis. And so they kind of have to come in direct contact with the pathogen, the cancer cell, the worn out cell, whatever they're going to eat, they have to actually come in contact with, wrap their little cellular processes around them. So you can see they look more like a sun in shape because they have all these long cellular processes that they actually wrap around. The invader, for example, the bacteria, the fungus, whatever it is, and ingest it. And so they have a lot of vacuoles and a lot of lysosomes in their cytoplasm because those food vacuoles or phagocytic vacuoles are ingested materials. And then they need lysosomes because if you remember, lysosomes are the major organelle for digestion, right? So they'll fuse the lysosome with the vacuole that has the bacterium in it, and then that'll digest the bacterium, right? Now, some of these cells, macrophages, for example, which are differentiated monocytes, can be what are called androgen-presenting cells. They call them APC cells. They can actually take pieces of the bacteria they just digested and insert them into their cell membrane and then go back to lymphatic tissues and present that bacteria antigen, that piece of bacteria, to other white blood cells to activate a specific immune response. So this is how vaccines work, for example, right? So when you get your flu vaccine, you're teaching your immune system new antigens. And they remember those antigens based on your shot. This is why the COVID shot hurt so bad, right? It made you so sore, made people so sick, because your immune system is really responding well to it. And then your immune system will remember that so that when you're exposed to COVID again and a white blood cell digests it and presents it to the lymphatic tissues, you get an immune response immediately, and you're not sick very long. Or not sick at all, right, after you get vaccines. So that's how vaccines work. Unfortunately, our government doesn't know how vaccines work, right? They're taking them all away. Or not making them mandatory. So measles is breaking out again all over the world. Isn't this really sad, right? Especially if it's your kid that dies. Ugh. Anyway, off my soapbox. Get your vaccines. Get your flu shot. Get your COVID shots. I still get mine. Or don't. Don't listen to me. So that's what phagocytes do. Now, the other types, like some of your lymphocytes, like B lymphocytes, and then eosinophils and basophils, they release chemical weapons. So eosinophils, this is probably one of the rarest white blood cell that you'll find in a blood smear, I should say, in the USA, right? In developed countries, because eosinophils fight parasites mostly. And so, we have really good sanitation here in the U.S. So there are no parasites in our water, in our food usually, right? We wash our hands, those kinds of things. If your eosinophil count is really high, then you have a parasite infection, right? So if you go visit Africa and come back and your eosinophil number is really high and you feel really bad, you probably have some blood-borne parasite that you get. So these are hard to find a lot of times in a blood smear from an American, for example. Basophils release histamine. All right, so basophils, they release the chemical histamine. And histamine, we're going to talk about histamine when we get to the blood vessels. Histamine causes vasodilation. All right, and so what does that mean? That means your blood vessel does this. It gets big. It opens up. And it's going to deliver blood to a place. Another cell that does this, that acts like a basophil, is called and I'll put it underneath so you can see it on the video. It's called a mast cell. Now, a mast cell is not a basophil, right? But it's like a basophil. Mast cells are just found out in tissue, and they release histamine too when they're activated. And what that causes is what we call inflammation, right? And inflammation is a part of the immune response. So, for example, if you've ever cut a finger and it kind of gets really hot and red, right? And you can feel it. The temperature's a lot different in your thumb, for example, where your cut is versus the rest of your body. You're releasing histamine in that area. And it's probably mast cells in that area or a basophil in that area that's releasing histamine. And all the blood vessels, all the capillaries in your thumb are opening up, right? And that's what causes all that heat. And the reason for that is to deliver blood to that area so you can deliver the rest of these white blood cells to take care of the infection that's happening in that place. Now, the B lymphocytes, so you got a couple different groups of lymphocytes, and I know this is not immunology, but you have T cells and B cells and helper cells and memory cells. You got a whole bunch of different types of lymphocytes. The T lymphocytes are phagocytic. All right, the T lymphocytes are phagocytic. The B lymphocytes are going to be chemical releasing. So B lymphocytes differentiate into what are called plasma cells. Okay, so a B cell becomes a plasma cell when it's activated. So we can go back to COVID-19. So, when they give you the shot and you get all sore or you get sick, the first couple of shots I felt like I had COVID again, right? I laid in bed for an hour, or a couple hours or a couple of days. What happens is if you were to take a blood sample of somebody after you give them the COVID shot several days later, their antibodies would go up for COVID, right? Their antibody count will go up. And then your antibody count stays high for a certain number of days. And then when you're exposed, then it'll drop, right? Back to zero. And then if you're exposed to COVID again, all of a sudden your antibodies go way up again, right? And so what happens is when you get that initial vaccine or you had COVID and your immune system fought it off, they remember it, right? These memory cells, when an antigen presenting cell brings in a piece of the COVID virus, which is what you're actually getting in the RNA virus, is the RNA code for a piece of the capsid of the COVID virus that your body makes, and then your immune system says, no, and responds to that, right? And that's what makes you sore or sick. They remember that. There are lymphocytes, which are called memory lymphocytes, and they're helper lymphocytes that actually remember the shape of the COVID capsid and sit in the lymphatic tissue waiting to be activated again. And so when you're exposed to COVID, and say a monocyte eats the COVID virus out in your body, it'll break up the COVID virus, insert all the pieces of it into its membrane, and deliver it back to the memory cells. And when that memory cell meets that antigen, it explodes into action and releases a bunch of what are called leukotrienes and cytokines, which cause mitosis of the plasma cells that start releasing the antibodies that destroy COVID. And that's why you respond really quickly to a vaccine. That's kind of how it works. And so these B lymphocytes, which are inactive, are kind of sitting around waiting. You got a bunch of different ones based on all the things you've been exposed to, based on the antigens that you got from mom a long time ago, right? And breastfeeding, and all the vaccines that you've had, all the things you've been exposed to, are stored in your lymphatic tissue so that those cells can be activated again upon exposure. Now, some vaccines you have to get a booster, right? And that's just reteaching those cells, because sometimes those cells don't last forever, right? They kind of have a finite life. And that's why if you've had the measles vaccine or if you've had polio vaccine, right? We don't even get that vaccine anymore, right? Because we eradicated the polio virus. But if it were to come back, we would all have to be vaccinated for it, right? So we hope those things don't happen. That's kind of how all of those work. Eosinophils, they release chemical weapons that blow holes in parasites, which I think is pretty cool. So it's like, it's like artillery almost that they're releasing that blows holes into things. That antibodies either grab onto or just bind to the surface of your bacterium, or grab onto the surface of a virus and immobilize it, or prevent it from binding to receptors, or sometimes blow holes in the bacteria also. So basically, hopefully you get from all of this that you have phagocytic cells, chemical producing cells that are kind of a military, if you will, in your body, right? That prevents invaders from getting into your body and wreaking havoc. They also destroy cancer, right? So this is why having a really good immune system, or boosting your immune system, helps with cancer not arising in your body. It's been estimated that cancers arise in your body all day, every day, and your immune system takes care of them, right? That's why older people or that's not always the case, but older people typically are more susceptible to cancers than younger people, because their immune systems are older or shot or immunocompromised people, right? So that's why they say get your sleep, drink your vitamin C, or eat your vitamin C, or boost your immune system. All right, so those are blood cells. Now, so we've talked about blood, we've talked about the hearts. I'll come back to the blood when we get kind of finished with this lecture, and we'll talk about kind of how hemoglobin works. But before we do that, I wanted to talk about, at least give you a basic foundation on how the arteries and veins work, and a little bit about how blood pressure allows for flow, and how our body deals with the degradation of blood pressure, which is going to happen in any system of pipes that you incorporate into a system, and the body's no different. Because we have a closed system of blood vessels, if we can get the blood moving, right, we don't have to have even pressure throughout the whole thing, if that makes sense, because it's all connected. If you're pushing blood on one part of your network of blood vessels, the other part's going to have to deliver the blood back, right? Because the part that's under high pressure, which we're going to call arteries, is forcing the blood into the part of the system that has very low pressure and pushing that blood back to the heart. And we know that veins, and I kind of mentioned this last time, that veins have low pressure, but lots of valves, which kind of help, right, with the effectiveness of returning blood back to the heart. So what I've done here is I've listed kind of the major blood vessels, right? So coming out of the heart and coming into the heart are the major arteries and veins of the body. And the best way, again, to define these blood vessels anatomically and physiologically are arteries carry blood away from the heart and veins bring blood to the heart, okay? Another really important physiologic difference between the two that's based on their anatomy, on what they look like histologically, arteries are pressure reservoirs. What I mean by that is they help maintain blood pressure the best that they can, right? And the way they do that is through their elasticity, their ability to expand when the heart contracts. So think about it. When your ventricle contracts, you're throwing a big glob of blood, right, into the aorta at high pressure. And so the aorta is going to receive it and stretch, right, as it receives this ejection of blood, this 65, 70 mils of blood, right, that are being injected from the left ventricle, for example. And so it stretches, and then when the heart relaxes, what's really nice about arteries is they return to their original shape, right, as the ventricle relaxes. And so think about it, what they're doing is they're pushing on the blood and preventing the blood pressure from just dissipating because they're actually squeezing, if you will, on the blood itself. And so arteries are either really elastic or they're very muscular. All right, so the further you get away from the heart, and this probably should make sense, pressure is going to slowly degrade, right? And here's the major reason for that. Is because as you move from the aorta to other arteries, those arteries are branching off the aorta, right? Which then branch again and branch again and branch again. What are they doing? They're getting smaller and smaller and smaller. Okay. Have you ever tried to blow through a normal straw and a coffee straw? Try it, if you haven't. So blowing through a wide straw is easy. Blowing through a narrow coffee straw is really hard. And that's because there's lots of resistance in something that's got a very small diameter. And the question is why? Well, I could give you the mathematics behind it, the physics behind it, right? I mean, it's pretty easy. I can show you the formula that you don't have to memorize. That kind of shows you the math. But in reality, things stick to the walls. So the lower the diameter, the less volume, the more time you're going to spend hitting the wall, right? And when you hit a wall, it produces friction. Right? So the wider and wider and wider you make something, the less time the blood's going to spend touching the sides. And so it speeds up because resistance drops. Does that make sense? That's the common sense explanation of it. But there's a mathematical model that shows you that as you halve a arterial, you're going to quadruple the resistance, right? And I'll show you an equation that shows you that. Now, it makes sense that arteries are actually pressure reservoirs when you look at them. So this is a vein, medium-sized vein right here. Notice it has a very odd shape, right? This is a medium-sized artery. Arteries are always nice and circular. They never change shape because they have a thick wall. Veins have very thin walls, and they're very elastic. They simply fill up with blood and kind of stretch, and when you empty them during histology, they collapse. Right? Arteries don't do that because of their thick walls. And the reason for that, and we'll look at the wall here right now, is because of the thickness of the wall and then what's found in the layers of that wall. Right? And so the wall is made up of layers. Arteries and veins have the same layers. It's just they're very thin in veins. And they give them names. They call them tunics or tunica. Is the name of each layer. And that means layer. It's just the scientific word for layer, right? And so you notice you have externa and interna And then you have a media, right? Which is in the middle, right? So you got an outer layer, a middle layer, and an inner layer, right? So you got tunica externa, tunica media, and tunica interna. And if you look at an artery and vein, they have the same three layers. The big difference is the media is really thick in an artery, right? The middle layer is really thick in the artery, right? And the media also, it determines kind of the function of the blood vessel. So, for example, if the media is filled with elastic connective tissue, like the aorta, you look at the aorta, it's all elastic. It can stretch and rebound, return to its original shape. If you go down to a medium-sized to small artery, the media is going to be completely smooth muscle so that it can squeeze on the blood, actually squeeze on it, which makes sense because the medium-sized artery is going to be further away from the heart, right? And by that time, blood pressure is going to start to degrade, right? And what you can do is squeeze on the blood a little bit, squeeze on the actual blood passing through, and try to help maintain that blood pressure for a longer period of time as you move down into the smaller and smaller arteries. So this is what you see. When you go from the aorta to a large vein to a medium-sized vein, the aorta, the largest blood vessel in the body, is actually called an elastic artery because that media is completely elastic connective tissue. It's like a rubber band. It can stretch and return to its original shape. As you move down from the aorta to, say, a small, large artery, I know that's a weird term, right? One of the smaller of the large arteries, that media will be about half and half. It'll be half elastic and half smooth muscle. And then as you move down into a small artery or a medium-sized artery, it's all smooth muscle. So you slowly replace the elastic connective tissue with smooth muscle so that the further you get away from the heart, the more you can kind of constrict, if you will, or squeeze on the blood. Now, in a vein, the media is just really thin. And so it doesn't really have a great ability to maintain its shape and to kind of prevent blood, if you put a big glob of blood in it, prevent from stretch. And it just can't really return back to its original shape. And so veins are actually known as blood reservoirs because at any one time, most of your blood is in the vein, right? And so they pull blood. They tend to pull blood or hold blood, a reservoir for blood. So that's why, remember when I talked about Frank Starling? If I get high venous return, I increase venous return, then I'm taking that pooled blood and sending it back to the heart. And then that's going to increase blood pressure, isn't it? Because it's going to increase volume. And so that will obviously, if I have a bunch of blood in the veins and I return it all at once to the heart, it's going to cause the atria and the ventricles to stretch more and they're going to contract harder, right? Based on that stretch reflex we talked about last time. Now, the externa is, pretty much the same in both arteries and veins, and it's connective tissue. What I like to think of the externa as is connective tissue saran wrap. We wrap the artery or vein, several layers of this wrap, and then we attach it somewhere. And so the externa is typically dense, irregular connective tissue, sometimes some fat, some adipose, and its glues and anchors our blood vessels in place. The interna is the endothelium and its connective tissue. All right? So the interna is the endothelium and its connective tissue. So for simplistic or just for our normal everyday talk, the externa and the interna are pretty much the same in arteries and veins. They're endothelium and connective tissue saran wrap. It's the media that's different in width and in what makes it up, right? In its composition. And so that's why the media kind of plays the role in determining whether a blood vessel is a pressure reservoir, whether it's a muscular or elastic artery. And the veins just have very thin walls and tend to pool blood instead of pushing it forward. Again, that form function thing is really important, right? What it looks like kind of determine what it does. Now, the smallest arteries in the body are called arterioles. So IOLES means little. So artery, little artery, right? So arterioles are the smallest arteries. And so they're going to deliver blood to capillaries. Arterioles do. And then the smallest veins are called venules, right? Which again just means small or little vein. And so the venules drain the capillaries. So remember, what connects arteries to veins are the capillary beds, right? Capillaries have the thinnest walls. They're only internal. So you remove these two walls, these two layers, and you only have the internal. All right, you only have the endothelium and its connective tissue. And if you think about that, that makes a lot of sense. If I'm blood passing through this artery right here, there is no way something can move from, there's no way that something could move from the lumen through that thick wall to these tissues here, right? I mean, it's just too thick. So I remove all of that stuff, and now I have an endothelium that I can now deliver stuff because it's very thin, right? We already seen how thin the endothelium is. The most common blood vessel in your body are capillaries. Remember, you have 60,000 kilometers of blood vessels passing through your body. It's a great Jeopardy question. It'll blow your parents away at dinner. Tell them that someday, right? Most of those blood vessels are capillaries. The other thing we're going to see is blood moves really fast through the arteries and veins and very slow through the capillaries. All right, so we got lots of speed because we have a closed system under high pressure, but things do slow down in the capillaries, which is good because not only are the capillaries thin, but the blood flow is slowed so that you get proper exchange. All exchange between the blood and the tissue or blood in the environment happens only in capillaries. All right, that's the only place you're going to exchange materials. So I actually kind of talk my way over. I do this every time I talk my way through all the layers. All right, so this is a nice picture of that. This is a cool image here. This is a picture of the aorta of a mouse. So it's small. And the yellow stain is a specific stain for elastic fibers. And so you can see the whole media is elastic there, right? And then you got a purple stain out here. It's eluting blue. So this is the tunica A, tunica adventitia, or the tunica externa. This is the media. And then the interna is this little kind of squiggly black line that you see, right? It's in direct contact with the blood. So that's a nice image of an elastic artery where the media is completely elastic connective tissue. What I do like about this figure is that it shows you kind of sizes of arteries and veins as far as their diameter. And it also shows you which layers are present. So when you get to the arteries and the arterioles and the venules, you reduce the externa and you reduce the media to one layer of smooth muscle usually, and then the interna. What I want you to notice is that the arteriole has a nice layer of smooth muscle, and it's going to play a major role in blood pressure and a major role in which capillary beds get blood and which don't get blood. So what I mean by that is, if you think about it, if you're 60,000 kilometers of blood vessels and most of those are capillaries, and you have 6 liters of blood, it's not a lot of blood. You can't just send blood to every capillary bed at once. You know what that's called? Anaphylactic shock, and you die really fast. You don't reverse it. So an allergic response, if people are allergic to peanut butter, for example, they usually have anaphylaxis, right? Where if they get exposed to peanut butter, all of their capillary beds open up at once, and their blood pressure plummets, and they go into a coma, and they can die from that, right? And so those types of allergies, like bee sting allergies or peanut butter allergies, or some of these allergies that are nut allergies that are really bad cause a mass release of histamine, is what they do, right? So if I release histamine everywhere in my body all at once, then all of the blood vessels that are really small, called arterioles, are going to open up at once and deliver blood, right? And so what do those people carry around with them? EpiPens, right? Which is epinephrine. If you inject epinephrine into your leg, epinephrine causes vasoconstriction of smooth muscle. So that's how an EpiPen reverses histamine. What I always tell a student is you should carry two. I know they're expensive as hell, because the first one you usually get to a person too early, right? They start feeling bad. You got to really wait till they're about to pass out before you get to them, because then they can get another wave of it, because if they're continually releasing histamine. So not only do you give them an EpiPen, you get them to the hospital, right? If they're really having bad problems. Benadryl also works for people that have allergic reactions, because Benadryl is an antihistamine. It blocks histamine. So that's how it works. So a lot of people will take a lot of Benadryl, right, which puts them to sleep, but they can reverse some histamine allergies that way. All good on layers and how the blood vessels work? Now, if we look at blood pressure overall. So again, this can get really complicated. I really encourage you to read your book on this part of it, just to, to fill in your notes and to make sure it kind of makes sense in your head. And I'm going to keep the explanation very biological, but there's a lot of math and physics that's involved with water pressure, with pressure in general. So remember, blood pressure is hydrostatic pressure. You're squeezing on water, which produces a pressure. This pressure needs to be high enough to cause flow, to cause movement. You guys have all been places where you have low water pressure and you're like taking a shower and it's dribbling on you, right? It's not a lot of pressure. What's happening is the pressure that's coming into that building is being hindered in some way so that the pressure's not high enough to push the water right through the pipes. The same thing here. If your heart's not strong enough to push water through the pipes, then blood flow is going to drop, and you're going to get edema and some things that are going to happen within the body. So your heart has to produce enough pressure to overcome resistance. And this is the easy formula here, right? So you get a change in pressure. And as long as that change in pressure is higher than the resistance of our tube, then you get flow, right? Now, there's something called flow and velocity, speed versus like just movement. I'm not going to go into that either, because then it gets confusing as hell. But if you ever really get into this, or you're on a medical school or whatnot, they'll give you the physics behind flow versus velocity, right? So you can imagine if I increase or decrease resistance, because think about it, your heart always kind of produces. Now you can produce more pressure, but your heart is going to consistently produce a certain blood pressure, right? Your blood pressure is pretty consistent, right, from day to day. So one way to kind of change flow is to mess with resistance, right? I could increase resistance or decrease resistance, keeping my pressure the same. The blood will move faster, right? Or it'll enter a blood vessel if the resistance is reduced. That's what the arterioles can do. The arterioles play this game because think about it. If I'm the smallest artery and I tell you all the pressures on the arterial side, they're the gateway to the rest of the circulation, aren't they? The arterioles? Because they're delivering blood to capillaries. So if they open wide open, they're going to deliver blood to the capillaries. If they close down, they're going to limit blood flow, right? And so you can imagine all through your body right now, you're tweaking which capillaries are receiving blood and which aren't based on metabolism. So right now you're sitting and you're listening. Your brain always receives the same amount of blood flow. Now, if you've ever had a class where you eat right before you go to class and you're trying to listen and you're like, got a boring teacher like me who's talking to you, you're like, oh my God, I can't stay awake. That's because your digestive tract is fighting your brain for blood. Because think about it, you got lots of feet of intestines. All of a sudden they want blood because you just ate a meal And all the blood goes to your gut, and your brain is struggling because you're not getting the blood it needs, right? So sometimes that happens. But if you get up and start moving around or start running, then you have to redirect blood, right? You got to take it away from the gut and the kidneys, send it to your skeletal muscle. But you're never going to really try to affect the brain too much. If you cut blood flow off to the brain, you pass out. So we have to play this game with changing resistance in certain places in order to deliver blood. So they not only act as the gateway to kind of who gets blood and who doesn't, the arterioles, but they can play a major role in blood pressure. So they're kind of the gateways to blood flow and can help with systemic blood pressure. Now, I'll talk about how here in a second, but if you look at this figure right here, this gives you biggest artery to capillaries to biggest vein, right? And they've got this representation down. So you big aorta branches down into smaller and smaller arteries that eventually become arterioles, and then they deliver blood to capillaries, right? And then the capillaries drain into venules to bigger and bigger and bigger and bigger and bigger veins until you get to the vena cavas, right? Look at pressure. Pressure's high on the arterial side and 0 on the big vein side. I mean, it really is. So all of your pressure's over here, which to me, I guess I didn't think about it. That confused the hell out of me when I first learned this. But you got to remember, this is a closed system. If you're pushing blood, even if it's 0 here, it's got to return. I mean, it's got to go somewhere, right? Because you're moving it. If this was not a closed system, it's just going to leak and then it stops, right? But because it's not an open system and it's closed, then you're going to have to deliver blood back. We also can use some muscle pumps over here, our skeletal muscle pumps, to kind of help with that pressure drop. And we also have valves that can move blood from one compartment to the next, right? That kind of helps in the extremities. But the big question for me was why? Why is pressure drop like this? Why doesn't it just stay uniform? And it all has to do with basically size of the blood vessel. Big, smaller, 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 smaller. The more time the blood spends hitting the wall of the blood vessel, and as you spend time hitting the wall, this blood is viscous. It's not just water. It's a pretty viscous fluid. It's hard to push, and it will stick to the walls, and that produces friction, right? And what's friction produce? What happens when you do this? Your hands get what? They get warm, right? And so that's exactly what happens. The pressure, because of the viscosity of the blood and the sticking to the walls, produces friction, which converts the pressure to heat, and it degrades, right? So that's why it's pretty high here for a little while, right? Because these are big blood vessels, and there's a lot less resistance. And then as they get into smaller and smaller vessels, when they hit the arterioles, they plummet because those are the smallest diameter arteries. And you converting all of that pressure into heat at that point. So as you deliver blood into the capillaries, you're pretty low on pressure because capillaries, think about their resistance. The highest resistance in this system are the capillaries because there are so many of them, lots of length, and they have the smallest diameter. So it's like pushing blood through a bunch of coffee straws. Think about that. That's hard, right? And that's why the pressure just plummets to 0 by the time you hit the capillaries. So as long as we keep blood, as I mentioned, kind of high on the arterial side, then we'll force the blood back, right? But you can imagine if I mess with this pressure too much, if I drop it too much, that's really going to affect return. All right, and it can have large effects on water pressure, right? On flow rate. It's going to be drippy instead of flowing, right? If we let that pressure drop too much. And so we have to, in some cases, if your blood pressure plummets for whatever reason, you have an allergic response to something, you're bleeding out, I don't know where I hope that's, you have internal bleeding, those types of things, your blood pressure starts to drop, your body needs to reverse that quickly and also permanently, right? Or it's going to be a bad thing, correct? And so we got to keep our pressure high enough to always overcome resistance. If our change in pressure is higher than resistance, then we get flow, which has a certain velocity. And I'll kind of describe velocity when we get to the capillaries, and it'll kind of help you picture how velocity works. Now, the nice thing about the cardiovascular system is it is closed. Because of that, flow remains the same at any one point in the circuit as long as the pressure hasn't changed too much, right? So even though the pressure's high here and 0 here, the flow rate here in these vena cavas, which are about the same width as in the aorta, are going to be the same. There's flow, consistent flow throughout. Now, when you watch blood flow in mammals, you get this kind of moving of blood like this with heart rate. In mammals, it's really small movement. Now, in an amphibian, you can really see it because their hearts and their blood vessels aren't as elastic and muscular as a mammalian heart and circulatory system. Our very derived circulatory system has pretty consistent flow rate throughout, as long as there's not blockage, right? Which can happen. So adding blockage increases resistance, which is going to decrease flow to that area. So coronary heart disease, a great example of this, can really hinder flow, right, to those areas, which is going to increase the pressure in those areas too, because as blood backs up. And what often becomes really dangerous with somebody that has a lot of plaque or a lot of high cholesterol and they're getting plaques everywhere is once those plaques kind of start slowing flow and blood backs up behind them, the pressure increases there, right? And they can break off. Like those plaques can all of a sudden, there's so much pressure on them, they break, and then they are flowing through circulation. So now you got this big piece of debris, right, flowing through circulation. And you can imagine when it gets to a capillary bed, it probably can block the capillary bed, right? And cause, an aneurysm, for example, in the brain, or something like that. So that's where these plaques become dangerous. Or we talked about blood clotting. If a blood clot forms in a closed blood vessel, that's really dangerous because that clot often is going to be broken off, right? And it'll break off. Big glob of clotted blood will then block blood vessels in other places, right? And can cause damage in those places. Okay, so pressure. Our pressure gradient's really high in a mammalian cardiovascular system. From the aorta, we have about 100 millimeters of mercury, and it's very low in the venous side, as I mentioned, and this is because of resistance. And if you look at this figure right here, this is why resistance happens. So resistance is increased by a couple of different factors. One is viscosity, how viscous a fluid is, right? Blood is pretty viscous. Now, mammalian blood is a lot more viscous than amphibian blood. Why? Because mammalian blood has more cells. The more formed elements you have, the thicker you are, right? The thicker the fluid. So it's harder to push our blood through our vessels than it is, say, a fish that has a lot less cells. The length of our system, all right? That is how many feet of blood vessels you have. And then obviously the diameter, this is, radius, all can affect resistance. Now, these two, in most of us, are typically held constant for the most part, unless you're really dehydrated, right? You can change your viscosity of your blood. Or if you change weight dramatically, like if you gain 20 pounds in 3 weeks and it's not fluid, that's impossible to do, right? But every pound of adipose that you add to your body adds about 10,000 kilometers of blood vessels, they say. So this is why your doctor's like, you could drop your blood pressure if you drop 10 pounds, right? I mean, that's 100,000 kilometers of blood vessels you just removed, right? Or if you gain a couple pounds and it's not water weight, and it's adipose or something, then you can obviously put pressure on the system, right? Does that make sense? That's why obesity is the silent killer. really affects blood pressure and whatnot. So these two in any of us are typically held pretty consistent from day to day. So it's this one that really we can work with, which is the diameter or the radius of blood vessels. And particularly it's at these arterioles because of where they're found and because that's where the major drop in pressure happens because they're the smallest arteries. So the other thing that the arterioles can do is I can open them up really wide or I can close them way down. And look at this next picture, which I think is a really cool picture. This is a wide open arteriole. That's a closed down arteriole. I mean, it's the same arteriole. Or it's not the same. It's the same, like in the same location where you've opened it up or closed it down right when it delivers blood to a capillary bed. That's pretty incredible. That delivers blood, that backs up blood, right? So you can see why locally, I really like to stress this, locally in the liver, for example, I can increase blood flow or decrease blood flow by just opening the arterioles in the liver. So I have control of local delivery, right? Local delivery. Or if I want to have a systemic effect, then I can control the diameter of all the arterioles at once. So, for example, in anaphylactic shock, I open them all up like this. And you try to deliver all your blood to every capillary bed. And that's when blood pressure plummets because it's just going to leave the arteries, right? There's going to be no blood in your arteries. It's going to be all in the capillaries. That's dangerous, right? But if you have a drop in blood pressure, your body will immediately react by closing down most of your arterioles. You'll get systemic arterial contraction of smooth muscle. And if you think about that, what's that going to do? If I go back to my figure that I just looked at, if I close all the arterioles down right here, then the blood is going to back up in my arterial system, right? Remember, if I increase volume in a closed system, it increases pressure. So if I close all or most of the arterioles down and back all the blood up, I'll get an immediate increase in blood pressure. So you can tweak. This is what your body does. You can tweak all day long kind of to help maintain arterial blood pressure. If it gets a little high, then I open up a few more arterioles, right? If the blood pressure drops for some reason, I get up too fast, you get immediate constriction of arterioles to kind of back blood up. And if you do that by tweaking kind of the diameter of the arterioles throughout the day, you can maintain very consistent blood pressure, right? Now, you guys have all heard about stress, how stress, lack of sleep, those types of things that increase the flight or fight response can really increase blood pressure and cause high blood pressure, right? And the reason for that is because epinephrine released either into the blood or by the sympathetic nervous system causes arterial constriction. And that can lead to, high blood pressure. So does that kind of make sense how you can do a systemic control of blood pressure and then local control of blood flow? So that's kind of how the arterioles play this role. And I give you this really ugly formula that you're not going to ever have to give to me. But this is kind of the mathematical formula for resistance. That's what that big R equals. All right, and there is a number in front of it. This L stands for length. This N stands for viscosity, right? Which is a constant. This constant you get based on the thickness of your blood. And then you have pi and then radius to the 4th power. So if you half an arteriole, this is more than half, but if this is wide open and this is closed, if you half the radius of an arteriole, you increase the resistance 16 times, 16-fold. 4 times 4, right? That's incredible. So just halving the diameter increases resistance so much that blood flow to that area is going to really stop almost and then back up. The other thing that I love about this image is this explanation right here that kind of describes velocity of blood. the wider your blood vessel is, the more of the blood that's in the middle, and the blood in the middle that has no touching of any of the sides of the blood vessel is going to be moving the fastest, right? And this is called laminar flow. This is the same thing of a river. If you've ever been on a bridge, if you haven't, next time you're on a bridge and you can stand on a bridge, if you look at a good sized river that doesn't have a bunch of rocks in it, if you look in the middle of the river, the water's moving really fast. If you move over closer to the shore, the water's moving slower. Why? Because the water on the edges of the river are hitting the bed, right? And the bed produces resistance, doesn't it? It's got rocks and mud and leaves and logs. And so you get slowing of the water on the edges, and the water in the middle is moving really fast right down the main channel. It's the same thing in a blood vessel. The blood that's hitting the walls is hitting the walls and swirling and slowing down, whereas the blood here in the middle of the vessel is moving unhindered, right? It's moving fast, so it's moving at the fastest velocity. So if you make this blood vessel smaller and smaller and smaller, less and less of the blood is moving fast in the middle, right? A lot more of it's hitting the walls. Does that make sense? And so that's why as you hit the walls, you produce more friction, and that pressure dissipates or degrades over time the further and further away you get from the heart, because your blood vessels get smaller and smaller and smaller. And you're releasing more of that pressure as heat. Because remember the law of thermodynamics, you don't create or destroy energy, you simply convert it from one form to the next, right? The two laws of thermodynamics. So you're taking pressure, a form of energy, and converting it to heat, and so it degrades. Does that make sense? Because of friction. Now, remember that whole cholesterol thing I just talked about? If you have high cholesterol and it starts building up on the walls, it's going to make the wall of the blood vessel first and foremost uneven, rough, and that's going to increase resistance, right? It's going to increase friction. And so that's why, high cholesterol is bad, because that, and it's not always just cholesterol, but it's other lipids. Remember, they're hydrophobic, so they don't travel through water very well, and they tend to accumulate on the walls of your blood vessels. And over time, if you have high cholesterol for 20 years, because there's no control of it, it can have a dramatic effect on pressure and flow and those kinds of things. Does that make sense? Hopefully I did that well enough. I always like to spend time on it because it really confused me when I was a student a long time ago. Well, I'm still a student, but back when I was young like you, which was a long time ago. So this is another representation from a different textbook that kind of shows you the same kind of scenario. But here we just have the arterial system, because that's the part that's under pressure, right? And what's really interesting, the other thing, and this always reminds me to explain this to you. One of the other major jobs of an elastic artery is to even out pressure difference. The ventricle, and you can imagine this, your left ventricle produces really high pressure and then really low pressure, because it contracts to a really small cavity and then opens up, right? So you get this really high pressure squeezing and then really low pressure as it opens. So the oscillations are humongous, right? Coming from the ventricle. You don't really want your blood going, you don't want these huge oscillations. And so what the arterial system does is it kind of does this, and it brings everything kind of back to normal, or it drops the oscillation size, right? That is the high to low pressure. So the pressure is more even. You still get this little kind of, pressure difference, but it's more even because of the rebound of the elastic elements of the blood vessels. And this is why when you take blood pressure, you have a high pressure, right? 120, and then you have a low pressure, 180. The 120 is during ventricular systole. The 80 is during ventricular diastole, right? So you do get a pressure difference. You can feel this, right? It's called pulse, right? If you do it on your neck or if you do it on your radial artery, you can feel that pulse if you're on an artery. Because if you're on a vein, you're not going to feel pulse as much because there's less pressure. So notice when you go from aorta to muscular arteries to capillaries, eventually when you hit the arterial, you plummet. This is really important because your velocity changes, okay? So here's where velocity becomes important. Obviously, if I have really high pressure here and I have a really wide blood vessel, the velocity of the blood in the large arteries and veins is really fast. All right, so not only do you have flow, but you have really fast flow. Like you can't see the blood cells under a microscope because they're speeding by. It's like you on a highway going 200 miles an hour and you can't see the trees. They're a blur, right? Now, as you get down into smaller and smaller blood vessels, the velocity slows. And then when you hit the capillary, this is what happens. You go from one blood vessel and then you spread all of that blood out into a higher surface area. So my analogy is the river main channel as you come down the Mississippi, for example, and then you hit New Orleans. And all of the river divides into smaller and smaller tributaries to become a delta, right? If you were to go into the middle of the delta and measure velocity, it would be really slow because you spread all that water out across a huge surface area, right? If I go back up into the main channel of the Mississippi and measure velocity, it's really fast, right? Because you're forcing all that water through a small channel, correct? Through a small riverbed. The same thing here. With these large vessels, velocity is really fast, but when I get to the capillary, I take all of that blood and spread it out over a really wide area, and the blood just slows down, right? And so it slows down in these smaller vessels because of surface area, what we call length, right? And diameter, which we remember is really small. And so blood flow slows really, really slow through the capillaries so I can exchange materials. And then when it drains into the venules and into larger and larger veins, it picks speed up again, right? Because you're forcing all that blood into a small tube and you're opening the tube up so your laminar flows more, your resistance less, and it speeds back up. So the flow in the vena cavas is just faster than in the aorta, even though there's no pressure there. And that's all because of you're forcing all that fluid into a small tube and your resistance is a lot less than those larger vessels. So the only, real place that for us, and I'm simplifying it, velocity really slows is in the small blood vessels, what we're going to call microcirculation, the arterioles, the capillaries, and the venules. Okay, questions? All right, so this last slide here summarizes all of that stuff. Talking about elasticity, muscular arteries, blood vessels, how elasticity leads to arterial recoil, compresses, maintains blood pressure, and smooths out pressure oscillations, right? Like we talked about. Velocity, how fast the flow is inversely proportional to cross-sectional area. Small cross-sectional area, or one blood vessel, equals high velocity, right? Large cross-sectional area equals low velocity. They're opposites, right? That's what inversely proportional means. And so you can see that in this figure. This is a cool figure. I like this figure too. So here's the arterial side. Here's the venial side. Here's the large aorta. Here are the vena cavas. And then your smallest blood vessels are in the middle, right? So these three right here, arterial, capillary, and venial, are what we call microcirculation because they're smallest, the smallest blood vessels. They also have the highest cross-sectional area, right? So they have the highest cross-sectional area. So this is basically area in red, right? So how much diameter you have. So notice it's really small here. And as you get to the smaller blood vessels, your cross-sectional area is at its peak. And then it drops back down. And look what happens to velocity. Really fast with small cross-sectional area. very slow with high cross-sectional area, and then it picks back up again. So that's a good like graphic representation of cross-sectional area to speed, right? So that's nice. That built-in way that the blood vessels work based on their diameter and length, or number of blood vessels in the capillaries, allows for slow enough velocity for exchange. Everywhere else, we want the blood to move really fast. We want to get it through, right? We want to get it through so we can get it back to the capillaries again. So that's why blood's moving really quickly and only slowing down, if you will, when we get to the capillary side of circulation. Make sense? All right. Let's do this last one, and then we'll save microcirculation for Tuesday. So this tells you the percent of blood in the typical mammal, how much of the blood is in vessels at any one point in time, like at stop time, right? So what I want you to notice is most of your blood is in the veins, right, at any one time. And that's why they're called, well, I call them, and like a lot of textbooks call them, blood reservoirs, because most of your blood, 60% of it, believe it or not, is typically in venous circulation at any one time. And everything else is kind of on the arterial side, right? So about 12% of your blood is always in the pulmonary circuit. The rest of it, 88% of it, is in the systemic circuit. And then some of it's in your heart, not very much, obviously, right? Some of it's in your systemic arteries and arterioles, and then your systemic capillaries, about 5%. So most of the blood sits in the veins for a long period of time. This is why, if I want to increase pressure, the easiest way to do that is to return all of that to the heart, and it'll contract harder, right? So that makes sense. So when I get up, I'm forcing blood with my skeletal muscle, squeezing 10% of this back to the heart that wasn't going to the heart. And so all of a sudden, you stretch the heart 10% more, contracts harder, and speeds up things for you. It's really cool how there's all this intrinsic control of you just moving around or changing your activity or behavior in the cardiovascular system. A lot of it happens intrinsically or automatically based on kind of how the system's built. It's kind of cool. So arteries and veins, arteries and arterioles are pressure reservoirs. Veins are blood reservoirs. Okay? All right, that's where we'll stop.